I think maybe probably they have some plan to it, but they haven't had really integrate into the FS. But what does the main voltage affect? Do you guys have any idea? Yeah, like okay, for example, for this CMMT AS, right, it's rated at a single phase 230 voltage. But what if I supply 120 volt? What will happen to my whole drive system?
I think it's just not enough on the DC bus.
No. What you say is partially correct. If let's say you are supplying lower, by right there will be not enough DC. But because our drive is actually DC rated, the low voltage is rated quite low. So if we look at the CMMT, right? Okay, you see our it's rated 230, but we can have a voltage input range from 100 to 230.
That means still
Yeah,
work.
yeah. So even like we supply 120 volts to the drive, we still can run it. There will be like under voltage in DC bus or whatever. But what do you guys think will be the effect? Whether you say like does that mean that my motor will not have enough torque, or like my motor I cannot run my motor as fast? Or what do you think is the effect that if let's say we put a lower like rated is 230, but if let's say I only supply 120?
I think the effect on the actuator speed, because torque will relate to the current.
Yes, that's right. So yeah, to be honest, I expect the answer from you as well, because Tuan, you had some experience with it. But let me just share maybe a graph from you, right? Let's talk about because for servo we don't have a graph, but for stepper we have this graph, which if you look at it, right? Yeah. As you can see here, this graph, okay? You can see that okay, we just ignore 1 and 2, we only focus on 3 and 4. You can see that for 24 volts, which is 3 this line, my maximum RPM is only around like 2000 something. Okay? But with 48 volts, this line, my RPM can up to 3500. Okay? So that means when you are supplying higher voltage, your drive can run at a higher speed. Okay? So and if we look at the catalog, right? The RPM here, this is the nominal rotary speed. Yeah. So nominal rotary speed in this case okay, in this case means that this speed is this 600 RPM is achieved with 48 volt. Okay, same as when you are looking at servo motor. So as you see here, the rated voltage is 332 volts. This is the DC bus voltage. So how you get the DC bus voltage? Maybe this is for more for Richard. Okay, when you supply the single phase voltage, right?
Yeah.
It's 230 volt, right? But 230 volt is a AC voltage. So what it does in the CMMT is that it converts this 230 volt to a DC bus voltage. And how do you know like what's the value that of the DC bus voltage is that you will multiply 230 with square root of 3. Okay, so multiply 230. So, square root of 2 or square root of 3?
I think 2.
I think 2, yeah.
Yeah.
Sorry for that.
Yeah.
Square root of 2. Yeah, so you multiply square root of 2, you will get the 335. Okay, so this means that like in Festo is all the rated voltage is the same level. So it's like the rated voltage for the drive is 230, and then here is 235, and you see all the data here, right? It is actually the nominal means that is when it's running at the rated voltage. But if you are more speed, you have more voltage, then technically you could have run at a higher speed. Yeah. Okay. Then just some information for the motor as well. You will see there is a nominal current, and then there's a peak current. Okay, so nominal, okay, we can show. I like to show with this graph because this is more clearly explained. Okay, so you see that we have a value called nominal torque. Okay, so nominal torque is which one?
Nominal.
I think it's this graph. Yeah, probably this graph, right? Is it this graph? No, okay, it's probably not showing. Okay, sorry, it's this graph, nominal. Okay, can you see that? I think it actually continues down here. Okay, this is a nominal graph. So what does nominal means that technically this motor, it can run. So it's a graph like of a speed, right? So when you are running at 1000 RPM, your motor current can up to let's say 0.55 K. You can run at 0.55 K for 100% of the duty cycle without any issue. So that means your drive can always run at 100 at this torque without any issue. So you have a peak torque of like 0.6 something. There's a gap here. So your motor, that means your motor can still go over this nominal current until the peak, but only for a short period of time, like maybe within 10 seconds or something like that. So and then the time is not clearly defined because it depends on how high you went over the nominal torque. Nominal torque and current is actually proportional to each other. Okay, so sometimes when we will say torque, sometimes we will say current, but it's just proportional to each other. What it means is that if let's say my nominal torque is 0.55, I will be able to go over the motor will be able to go over the nominal torque, like maybe running at 0.56 for a longer period of time. Just as an example, maybe I can run it like at 0.56 torque. I can run it at for 100 seconds. Okay. Yeah. But if let's say my torque go up to 0.662, for example, okay, perhaps I can only run it for like 10 seconds long, or maybe shorter, 5 seconds. Okay, then if let's say you still continue running with this high torque, right, then you will have an error, what we call it like I square T. So I square T is basically current times time. That's why as I mentioned, like the higher the current, then the lower the shorter time that you can run over the nominal current. Okay? You get it?
Actually, in the application, we need the motion profile, right? And then we can write the average like a torque.
Yes, that's right. Yes, that's right. That's why actually for Festool, we have something called the electric motion sensing tool. Okay, so for these tools, it will help you to identify like what are the Festool products that is suitable for your motion profile. Because customer requirement could be like, I want it to run at 0.5 meter per second with like maybe 10 kg load, for example. Something like this. So this one, I wouldn't go deep inside, just to let you guys have an idea that we have this kind of setting tools to make sure that, okay, what the customer motion profile actually can be run with the hardware that we suggested here. Okay, we'll come back to here later. Okay. As soon as I threatened to close it, it managed to open. Okay, so this is the graph. So if we look at the motion profile, right, this is how it will move. And if you look at motion characteristic, you can see that yeah, we are actually running at the peak top already. But you can run it at most of 100% of the time because it's still under the nominal top. So you see that this gray line is the nominal top, and then this blue line is the peak top. So with this RPM, with the speed that we want it to run, we are actually running at the peak top already. But it's still possible to run it. But if let's say customer is wanting to run at a higher speed, then probably this set of drive could not support their application. Okay. Then next we have the intermittent circuit voltage here. So this is because for our CMMT, right? Okay, so for our drive, right, if you it's not necessary. It's not the must that you use the main power supply, like the single phase AC or three phase AC. You can also supply straight away with the DC link circuit voltage. Okay, but of course when you are supplying a DC link voltage, then you cannot supply like this together. Okay, so only one of it. But it's possible that we can straight away supply just now we mentioned like 230 volt is equivalent to 335 volt DC, right? So if let's say customer do have the facility, they can also straight away supply the 335 volt DC to this port to power up our CMMT. Okay?
So the DC one is gonna be 325.
Yes,
And
correct.
the L1 and N is gonna be
220. Yeah.
yeah.
But it can be lower as
AC?
well. Because AC, yes. It can be lower because our input range is just now as you mentioned,
Yeah,
is
like 100.
100 to
Yeah.
230. Yeah. Okay. And then of course this is talking about single phase. If you are using for three phase, then voltage supply is different, but you can do the calculation yourself. Alright. So then with this, right, it also means that we can actually share this DC link between two of our CMMT. Yeah, so this is like for power saving, and why is it power saving? Then we'll get to now to the what we are going to next is external braking resistor. Okay, so I think Tuan, you might know what's the function of braking resistor. For Richard, do you have any idea?
Yeah, I just asked her about this.
Okay, good. Okay, so you know it already. So because when we want to decelerate our motor, it actually the motor will act like a generator and then feed back the voltage back to our CMMT, and then it will rise it will cause the increase in our DC link voltage. So if let's say you have a higher load, right, when you decelerate, it will generate more voltage. Then your DC link will have a higher voltage, but you know everything has a limitation there.
Yeah.
So we can't expect like the CMMT to store like DC voltage up to like 600 DC or 700 DC. There's a limit, probably around 400 something. Okay, so when you exceed this 400 something, right, you would have an error on your drive.
Yeah.
That's why we need the external braking resistor to sort of like to throw out the excess voltage. So the excess so to keep it at a certain level. So another option, as I mentioned, is not because we can share the DC voltage. So without if let's say you don't have a braking resistor, and if you have two drive and they are running at a different time, because when you are accelerating, you are actually using more of this voltage, so your voltage will drop. When you are decelerating, your voltage will rise.
Yeah.
And if both of the drives are moving at the opposite sequence, right, then you can share the DC link voltage. Yeah. So this is one of the like, energy saving things that our CMMT
I
can
guess
do.
one of the project using like this, test bed, one for generate torque,
Yeah.
and one for
Yes.
like load,
Yeah.
very big.
Yes,
So
correct.
using like a modular drive.
Yeah. Okay, so that's also something that our CMT can do. And in the braking resistor, we like when you do the motion profile, right, it will suggest you which is the braking resistor that you want to connect. And I saw you have a CMT just now, right?
Yeah, this one.
Okay. Thank you, Jimmy. So actually, in fact, all our CMT, right, it has a built-in braking resistor. This is a built-in braking resistor. So the spec you can look at the catalog. There is a minimum spec of it. So if let's say you want to connect the external braking resistor, then you'll be connecting to here, and you need to take out the internal, and then you connect to the external braking resistor. Okay. So get back to you. And for braking resistor, it's not like you can connect any braking resistor you want, because there is some limitation with the braking resistor also. Like if you look at the catalog here, for example, the C238, right? You can only connect the braking resistor with resistance from 100 ohm to 160 ohm. If you are connecting like the braking resistance lower than this value, right, then you will probably get some errors such as like the short circuit error or something like that. So you when you need to connect the braking resistor, you need to check on this specification and make sure they are suitable.
So like you said, like if I have two servos, one is accelerating, one is decelerating. We can connect the DC port together to stay finished.
Yes.
The
Correct.
DC plus and DC minus.
Yes.
Oh, okay.
Okay, so then application data is nothing much. As I mentioned, this one will affect the closed loop calculation of your drive. So if you put 5 kg here, you see that you say that the closed loop will recalculate so that it's a suitable closed loop for the 5 kg. And the multi-position will also accept, because when you are horizontal, you do not have a offset current when you are power stage. But when you are vertical, right, vertical axis, there is already you need a certain offset torque for the calculation. Yeah. So that's why when you put a vertical axis, then you can see there will be certain value in the offset torque. Yeah. But if you put horizontal, it's okay, right? Then we go to Q bus. As I mentioned, there is some configuration here. This one, if let's say your this switch you are set to all to 0, right? In this case, like you see here, all the switch is 0, 0, 0. Then you can change the configuration in your CMMT. But the thing is, when you change it, right? Like for example, if I need to show this online. This is so cute. You haven't used it?
No. Just take it out.
Okay. So as you see here, currently the active connection here is Ethernet IP and Modbus TCP. Okay, but when I change it, you will say the configuration next is Ethernet. But active is still Ethernet IP. So because every time you change the Fieldbus configuration, you will need to power cycle it. So you need to store and power cycle. And then in the EtherCAT, each of the Fieldbus here, there is some configuration that you need to set. But this one I will maybe we can discuss later on. Yeah, this is for the Fieldbus. This will be connected with their safety, but that one we will discuss about later. So this one is I/O also nothing much. So okay, this you can look at it yourself. And then if we go to motor, you can see the motor spec that you have configured here. So what is the nominal voltage for the data that is available here. Then you also have gearbox. Nothing much, it's just your gear ratio total, and then we have an axis here. axis here you have more things to configure, such as what is your homing method. Okay, after this page I'll talk about homing method and then whether you want to move to axis 0 point and what is a homing parameter. So this means that when you are doing homing, what is the speed that you want to run with the homing. Then we have homing timeout, like if let's say your homing is not completed within this 60 seconds, then you have an error, as well as what is the nominal current. So later I'll explain further on this. Then we also have the software limit, whether you want to reverse the dimensions, and there is a user-defined limit here. So the limit here means that if let's say my configuration now is like negative 1 to 1. Okay, so I have basically I'm giving a limit to this controller that my actual speed cannot be faster than 1 meter per second. So even though like if let's say I have a record table to ask it to run at 5 meters per second, the speed will just limit at 1 meter per second, so it will not go further than the same. Go with the torque and current, it will not go higher than this value that we have set here. Okay. Then we have the homing method. I think Richard Tuan would probably know about our homing method.
Yeah, and that's
All of them. All of them.
just one of them.
Okay.
Because I don't have the home sensor, so
Yeah, but I think the homing sensor is homing method is quite a standard. It's quite standard across the industry. So we have more or less the same homing method, but you can still just follow me to see if let's say maybe there's some difference. I don't know. Yeah, but at the same time I want to show to Richard what are the homing method that we have. You see there's a lot of selection, but the idea is straightforward. Okay, so we have all the homing methods here. Okay, this is all the homing method that we have. But let me go through one by one. First thing is we have a current position homing method. So current position is straightforward. So it means that we will just take the current position. So whatever position the drive is at right now, that point will be the 0 point. So it was 0 mm will be that at the current position. Okay. Then next is current position with 0 pulse. So current position means that it will start from the current position, but it will move to the 0 pulse. So for example, if your current position is here, and your 0 pulse of the motor is here. So take note that one motor, for one rotation, there's only one 0 pulse. Okay? So if this is your 0 pulse, when you trigger current position with 0 pulse, so it will move from your current position either to the positive direction or negative direction. The positive and negative direction depending on your setting, because there is a current position with 0 pulse to negative or positive direction. So if let's say you are positive direction, right, it will move. Yeah, it will positive and negative. If you will move to this point and then consider this as the 0 position. Okay. Then we also have a limit switch or reference switch. So limit switch and reference switch is depending on where is your, like, okay, if let's say my switch is here, whether my positive limit switch is here, negative limit switch is here, or the reference switch is here. So it will move to the switch position and then consider here. Okay, it will move to the here when it detected, right? When it detected the switch, then it will move to the opposite direction. Okay, so it will move slightly to the opposite direction until you no longer detect the sensors. Then that will be the position, 0 position. Okay. So then we also have the 0 pulse. So it's the same thing. You will move to the switch and then move to the opposite direction until you reach the 0 pulse. Okay. Then we have a positive and negative stop. So this is more straightforward. It will just keep on moving until something is blocking it, and then because when there's something blocking it, right, your motor current will rise up, and it will rise to this nominal current limit value. So that means this is like 30% of the nominal current. When that means when your motor reach 30% of the nominal current, it will consider here as the 0 position. Okay. And then same with 0 pulse, it will move here. Let's say negative stop with 0 pulse, it will move here until you reach the current. Then it will move to opposite direction until you reach the 0 pulse. Then here will be considered as the homing position. Okay, so that's all for the homing method.
The 0 pulse is fixed for every servo, right?
Yes, but they are not always at the same position. Yeah. So for example, 0 pulse for this motor and the other motor could be different. But there is it will be fixed for as long as you don't change the encoder or whatever, it will always be fixed.
So can we like change the? You can.
You can't change the 0 pulse of it. But what you can do is after you move to the 0 pulse, you can configure an offset. Because offset means that instead of here as a 0 position, I want to have an offset of 3 mm. I will move from the 0 pulse to forward 3 mm, and that will be my 0 position.
Yeah. Okay.
So Richard, later you can try this. You can try with all the different method on the theory, and then you can. You understand more about it.
Yeah. So it's really similar to what I.
Sorry?
Really similar to what I have done with other.
Yeah. Because it's a standard. It's nothing much.
Yeah.
It's just one. I think all the drive probably have the similar homing method. Okay, then we have the record table where you can configure like what is the call or whatever as mentioned here. Okay, then we also have a monitoring function. So monitoring function is to make sure that, because our drive is a closed loop control, so we need to make sure that your actual position except for the position is within this limit. So if let's say your actual position is out of this limit, right, then you will get out of this time, then you will get an error saying like following errors or things like this. You can also configure like when do you consider it is at a standstill, like as long as it's within this window position, within this velocity with this much of time, then it will be considered it the drive is at a standstill. Okay, then we have a closed loop here. Closed loop is when if let's say you couldn't, sometimes when you have a heavy load and you couldn't get the moving profile you want, right, then you can also actually adjust the gain, the PID gain or gain integral and there yourself with whether it's a positional control or velocity control, that you can change the closed loop for the drive. Okay, then we also have auto tuning. So normally, if let's say there's something like customer couldn't reach the movement profile, right, we will recommend them to do a auto tuning first. You put some errors. So auto tuning is you just need to start the auto tuning, right? Then the drive will vibrate itself to get a tuning suitable for this drive. Later on you guys can try. And there is these are more the advanced functions, so we can discuss this later on. And there is a manual movement tab. This manual movement tab is where you can change the manual movement function. So like what is the velocity that if I'm moving it manually, like when I jog it, right, then I can change the manual jog mode velocity here with a different kind of acceleration and velocity, or it's all here. Okay?
Have a master slave.
Sorry?
Master slave.
Master and slave means that we can have a hardware synchronization between our master and slave, but we don't do it now. It's more to advanced one. Maybe you guys can try. Actually, I don't know. How well do you guys understand the CNNT now? Like at least the basic function you can use it to run, and no issues already. So you can do all the functions in the CMMT already.
Pretty much.
Other than the advanced one.
Yeah. If something is bad, let's just skip at the moment. We need to let Richard understand.
Yeah. For Richard, anything you are still unclear about the drive, or is it clear for you as well?
Yeah, it's clear so far.
So far, okay.
Yeah.
You don't have to this just is going to be okay, then maybe if let's say Richard is clear, next Richard can try to connect the drive with our PLC. So from our Festo PLC, there's actually two ways you can do it. One is using Ethernet, but we don't use the soft motion first. Maybe you can try with the point-to-point movement. As you know, we have an application. You just follow the point-to-point movement on how to control the CMMT with our PLC. After you try with Ethernet, there is also one thing that you can try is using the Modbus TCP. Okay, so Modbus TCP it's actually for Modbus TCP or Ethernet IP, right, communicate with our drive. Okay, the